Hi guys, welcome back. This is an example of using partial fraction decomposition whenever your denominator has linear non-repeated factors. First of all, if this was my integral and it was presented to me, I would ask myself if basic rules applied, and then I would ask myself if U-substitution applied if my basic rules don't apply. Clearly, my basic rules do not apply because we don't have a quotient rule for antiderivatives. And we certainly don't have a rule like this in our table where you've got a polynomial over a polynomial. So basic rules do not apply here. Next, I would check U-substitution. And to check U-substitution, first I need to find an inside function. There are no parentheses. So in that case, if there's a fraction, usually use the denominator. So if I were to use U-substitution here, U would be x squared minus 3x. To check to see if that works, I need to take the derivative of U. So U is the denominator, x squared minus 3x minus 10, and du is derivative of that. So 2x minus 3, don't forget to multiply by dx. Now, if I can multiply this 2x minus 3 dx by something and get the 7x minus 14 dx, well then I'd be good to go. Then this would be a U-sub. But I can't multiply this by a constant and get 7x minus 14 dx back. So U-sub fails. We tried U-sub, it doesn't work. So at this point we're going to try partial fraction decomposition. Notice also that the degree of the numerator is 1 and the degree of the denominator is 2. Since the degree of the numerator is less than the degree of the denominator, we can go right to partial fraction decomposition immediately. We don't have to do long division first. Since the degree up here is less than the degree down here. Alright, now whenever you're doing partial fraction decomposition, the first thing you need to do is factor your denominator as much as possible. And so we've got x squared minus 3x minus 10. Since the leading coefficient is a 1, first times first has to be x squared. So I'm going to have an x times an x here to give me an x squared. And to figure out what these, there are going to be two numbers here, a number here and a number here. To figure out what these two numbers are, I think through possibilities. I'm looking for two numbers that give me a product of negative 10 and have a sum of negative 3. Now two numbers are going to have a negative product if they have opposite signs. A positive times a negative is a negative. So what I'm really looking for is two numbers that multiply to give me 10 that have a difference of 3. Well, 2 and 5 will work as long as one of these is negative. In order for the sum to be a negative 3, the 5 has to be negative. Negative 5 plus 2 is negative 3, and negative 5 times 2 is negative 10. So this is x plus 2 and x minus 5. So our original integrand can be written this way. It's 7x minus 14 over x plus 2 times x minus 5. Now that that denominator is factored, I'm ready to state the partial fraction decomposition. And I'm going to leave a lot of space because I'm going to multiply this equation by something in just a minute. So first I notice I've got a linear factor, it's not repeated, so I get a constant over that factor in my decomposition. And then I've got another linear factor. It's not repeated. So I get a constant over that factor in my decomposition. Then, in order to find a and b, I'm going to simplify this equation. And I'll simplify this equation by multiplying by the LCD. Now the LCD is always the original denominator. So we're going to multiply by the LCD, which is the original denominator, and then simplify. So we multiply everything by x plus 2 times x minus 5. And this term gets multiplied by x plus 2 times x minus 5. And this term gets multiplied by x plus 2 times x minus 5. And that, I remember that that's all in parentheses. That whole thing is being multiplied by that. And then I simplify where I can. Now if I've chosen the correct LCD, all of my denominators should be gone. X plus 2 divided by itself is 1. And x minus 5 divided by itself is 1. So those guys are gone. And x plus 2 divided by itself is 1. So those guys are gone. And then the x minus 5s are gone. So after simplification, we end up with our original numerator, 7x minus 14, is equal to a times x minus 5 plus b times x plus 2. Okay, now this is a little bit of a problem. We're trying to find a and b. So I can think of this as one equation with two unknowns, a and b. Or I can even think of this as one equation with three unknowns if I'm thinking of x as an unknown as well. But remember, we're trying to find a value of a and a value of b. Then when I substitute a and b in here and simplify this, I get 7x minus 14. So this is one equation with two unknowns. In order to get it down to one equation with one unknown so that we can solve for a, or one equation with one unknown so that we can solve for b, we're going to do the following. You're going to choose the value of x. I'm going to say values of x that make each factor 0. The factor in the LCD, the x minus 5 and the x plus 2. And substitute those into the equation. You're going to do that twice, one for this factor, once for this factor, and once for this factor. And then you're going to solve for a and b. Okay, so here we are. Now, in order to make this factor 0, x would have to be 5, because 5 minus 5 is 0. If you prefer, you can set x minus 5 equal to 0 and solve for x by adding 5 to both sides. I hope that most of you guys, and by Calculus 2, can just look at that and see that x equals 5 will make that 0. So I'm going to choose x equals 5. I'm going to substitute that into both sides of the equation. When x is 5, I have 7 times 5 here, which is 35, minus 14, equals a times 5 minus 5, plus b times 5 plus 2. You do not have to show all of these steps every time, but I wanted to show you that that's literally what I'm doing. I'm literally substituting. I'm replacing x with a 5. I'm plugging that in. And then everything will simplify from there. So normally I would do all this arithmetic in my head, skip that line, and go straight to this. When x equals 5, I have 35 minus 14, which is 21. And that's a times 0, which is 0. And then I have plus b times 7. Isn't that nice? I substitute in x equals 5, that guy's gone, and I end up with 21 equals 7b. So now I can just solve for b. So b equals 21 divided by 7, which is 3. That's great. I got my b. Now, in order to solve for a, I want this factor to be 0. So this guy would be gone, and then I'll just have a times a constant equals a constant. To make this guy 0, x would have to be negative 2. So we get 7 times negative 2 is negative 14, minus 14, equals a times negative 2 minus 5 plus b times negative 2 plus 2. And that's 0 by design, so normally we skip this step. Normally we skip this step as well. We get negative 14 minus 14 is negative 28, and negative 2 minus 5 right here is negative 7. So we'll just divide to get a by itself, and we get a equals 4. All right, so now you're going to substitute these back into the form of your partial fraction decomposition. I know this line is a real mess, but that's why I did it in a different color. You can see we said this, which is our original integrand, is equal to this over this plus this over this. Now I know the value of a and b that make that equality true. When a is 4 and b is 3, this plus this equals this. So I'm going to substitute. So our original antiderivative is equal to this. It's a over x plus 2, and a is 4, so I substitute that in, plus b over x minus 5, and b is 3, so I substitute that in. Now you're not done yet. You still have to evaluate the integral. So after you've found a and b, you substitute a and b into the partial fraction decomposition, into the form of the PFD that you found earlier, and anti-differentiate. All right, so we're here. Now that can be solved with a simple U-sub where you use the denominator, and that can also be solved with a simple U-sub where you use the denominator. So we'll just do that. Because I got two different u's, I think I'm just going to split this into two integrals. You don't have to, but I'm going to factor out the 4 and the 3 as well. So this is 1 over x plus 2, and that's a 1 over x minus 5. The 3 has been factored out and the 4 has been factored out, but if I multiply straight across, 4 over 1 times this is 4 over x plus 2, and 3 times this is 3 over 1 times x minus 5. So this is equivalent to this. Now I'm all set for my u-subs. On this one, u is equal to x plus 2, and du is just 1 dx. So that's u, and that's du. On this one, u is equal to its denominator, x minus 5, and du is just 1 dx as well. So that's du. All right, so we've got the integral of this is equal to 4 times the integral of 1 over u du. And we've got a rule for that. That's the natural log of the absolute value of u. Plus c. We'll let the second term handle the plus c. And u was x plus 2, so I can substitute that in. And over here, I've got 3 times the integral of 1 over u du. When you do partial fractions with linear factors that are not repeated, you're going to see these logarithms a lot. So we've got 1 over u du. The antiderivative of 1 over u is still natural log of the absolute value of u plus c. It's a different u than over there. So I'm doing that little dotted line. And then this time, our u was x minus 5. Oops. I'm going to do that in a different color. X minus 5. All right, so that's our answer. Now we are done with the partial fraction decomposition part. I would like to verify some of this though. If I take the derivative of this, I should get this back. And if I get a common denominator here, I should get this back. So there's a lot of equivalencies to check, but we have already executed the method, followed the method perfectly, and gotten to this answer. Now, there's just a little bit more algebra that we can do, that we can discuss to show that our answer is equivalent to other answers that may be in the back of the book, and to show that our PFD actually did give us what it was supposed to. This is supposed to be equal to this if we've done everything correctly. So I'm just going to check our work on the next page, but if you want, you can stop here. We're done with the partial fraction decomposition part. All right, so this was our answer. Now, some of you might say, Miss Townsend, my answer does not look like their answer in the back of the book. Why do they have it? Why does theirs look different from mine? The reason their answer may look different from your answer is because they're using log properties. Now, here are 3 log properties that come in handy. We use them a little bit in differential equations as well. We use log and exponent properties a lot just to get y by itself. And to simplify expressions whenever we're solving first order linear differential equations. So this is a good review. If you have a constant in front of a logarithm, you can bring that constant inside. That's log of a to the n. So if I have a 4 out here and a 3 out here, this is our answer. But if I wanted to, I could take this 4 and I could bring it inside, and I could take this 3 and I could bring it inside. So this is equal to this. Natural log of the absolute value of x plus 2 to the 4th plus natural log of the absolute value of x minus 5 cubed plus c. Now be careful here. You don't want to cube the x and the 5. That's not x cubed minus 125. That's not what we do here. You're taking the whole thing and you're cubing it, just like we did here. You're taking whatever is inside that log and you're raising it to the nth power. So we've got this here. Now this is probably not what you see in the back of the book. If you didn't see this in the back of the book, you probably didn't see this in the back of the book either. They probably went even further with this. If I have a sum of 2 logs, so I've got log of something plus log of something else, and there's a coefficient of 1 out front and a coefficient of 1 here. Only when there are coefficients of 1, I can add those 2 logs together, and it turns out that I get the log of the product of a times b. If this was subtraction, if this was a minus sign instead of a plus sign, sometimes they'll use this rule. Log of a over b is equal to this. So it's log of the numerator minus log of the denominator equals log of a over b. So for this one, I might stop here. That'd be fine for a test or a quiz, but if I'm trying to match the answers in the back of the book, they probably use this first property to bring those inside, and they probably use this second property to write this as a single logarithm. And the absolute value of x plus 2 raised to the 4th is the same as x plus 2 to the 4th. Any number to the 4th, whether it's positive or negative, is still going to be the same thing. It's going to be positive when we raise it to the 4th. So I don't really need the absolute value bars there. So this is my a, and this is my b. And according to the rule, this is log of a times b plus c. So that may be the answer that's in the back of the book. Okay, but this is fine for us. A couple of things that I would like to check. I'd like to check that when I take the derivative of this, I get the right thing back, and I want to check that my partial fraction decomposition is actually equal to the original expression that I started with. So let's first check our antiderivative. if this is truly the antiderivative of our function, we should be able to take the derivative of it and get the integrand back. The derivative of the antiderivative should be the original function. All right. In order to do this, you have to remember this rule. The derivative of natural log of the absolute value of x is 1 over x. Just keep that in mind, and you might also need the chain rule. If you have the derivative of f of g of x, that's equal to the derivative of the outside. So find f prime, evaluate it at the inside. So put your inside function back in, and then multiply by the derivative of the inside. Okay, so here I've got 4 times the log of a function. So it's 4, bring your constant down, and multiply by the derivative of the log. The derivative of log of a function is 1 over the function. My function is x plus 2 times the derivative of the inside by the chain rule. And then here I'm adding 3 times a different log, so I'm going to have 3 plus the derivative of log of x minus 5. It's 1 over the inside function, so that's x minus 5, times the derivative of the inside. And the derivative of x plus 2 is 1, derivative of x minus 5 is also 1. So we end up with this. 4, if you want, you can write that as a fraction, and that as a fraction. This is 4 over x plus 2 plus 3 over x minus 5. Was that our integrand? Yes, it was. It was exactly what we got from our partial fraction decomposition. That's a very good sign. Now, I claim that this integrand is equal to that integrand. We said that by using partial fractions, this was equal to this. Let's check it out. Let's make sure that that's actually true. Let's make sure we didn't make any algebra errors. Sometimes if you make an algebra error, those constants might not be the right thing. So let's check it out and make sure. Okay, in order to write this as a single fraction, I need a common denominator. And the LCD in this case is just the product of the two denominators. So I've got an x plus 2 there and an x minus 5 here. I'm just going to multiply those two guys together, and that's going to be my LCD. If they had a factor in common, there might be more work to do in finding the LCD. But this time they don't, so you just multiply them. Now, in order to make this new denominator, the common denominator, x plus 2 times x minus 5, I need to multiply by x minus 5. And that's legal. I can do that to the denominator, as long as I also do that to the numerator. Because I want to multiply the whole thing by a 1. I don't want to change the value of my fraction. If I just did that to the denominator, I'd be changing the value of my fraction. It'd be a totally different fraction. It's not legal. The same thing would be true if I just multiplied it to the numerator. Not legal either. But if I multiply the numerator and denominator by the same thing, this is exactly equal to what it was when I started. Well, not exactly equal. There's an issue at x equals 5, but we're not going to worry about that here. Okay, so this is going to be an equivalent expression as long as x isn't equal to 5. And we'll have a common denominator. We're going to have an x plus 2 times x minus 5 down here. Now over here, I want that denominator to be x plus 2 times x minus 5. So I'm going to multiply it by the missing x plus 2. It's legal as long as I also do the same thing in the numerator. That means I'm just multiplying this by 1. So it's going to have the same value as long as our denominator is well defined and all that jazz. So this is equal to the 3 over x minus 5 when it's well defined. So this has the new denominator and this has the new denominator. So let's multiply them, see what we get. I'm going to distribute my 4 and distribute my 3. So 4 times x is 4x. 4 times negative 5 is negative 20. 3 times x is 3x. 3 times positive 2 is positive 6. All over x plus 2 times x minus 5. First times first is x squared. Outer times outer is negative 5x. Inner times inner is 2x. And last times last is negative 10. Claim is that's equal to my original integrand. Let's simplify. 4x plus 3x is 7x. Collecting like terms. Negative 20 plus 6 is negative 14. That's promising. X squared doesn't have any like terms, so we leave it alone. Negative 5x plus 2x is negative 3x. And then the negative 10 comes down. Isn't that our original integrand? It is! That's very exciting. That means we did it right. Yay! Woohoo! So the derivative of our antiderivative was equal to our partial fraction decomposition, and once we got a common denominator, we saw that that was equal to the original integrand. So the derivative of the antiderivative is equal to the original function, and that means we correctly used partial fraction decomposition to find the antiderivative of this guy.